Okay, so hello everyone. So we will have this webinar today. This webinar will be about how to enable mixed precision in CFD, computational fluid dynamic codes, with the help of tools. And the tool is developed in University Versailles Saint-Quentin, which is part of University Paris-Saclay by Pablo de Oliveira Castro, professor at that university, who is also responsible for master program in HPC. So, and the idea is like, since we are used to developing codes in HPC codes and to spend quite a bit of time in profiling and optimizing it. So the idea here, why not to use a tool that will help us with some confidence to reduce precision of our computation. So that's the main message here. And so Pablo will present the tool and what is behind, and I will talk about experience from the CEEC project, what we learned, how it worked for us, and so on. So the first part would be delivered by Pablo. Pablo, you can share your screen and go ahead with your presentation.
Yeah, can you see my screen?
Yes. And we
Great.
can make a full screen so that we will see one slide per page. Oh yeah, lovely. Go ahead.
Thank you very much, Roman. So let me start first by saying that I'm indeed one of the main contributors of this tool, VerifiCarlo, but it's an open source project. You can find it on GitHub, and it has many active contributors from different institutions. So that we have contributors from Intel, we have contributors from University of Perpignan, we have contributors from University of Concordia. So here on the first slide, I just put the logo of my institution because I'm speaking for myself, but it's really a collaborative project, and there are many people who contributed to it, and they are acknowledged in the last slide. So yeah, first I'm going to start with a bit of context. When you are building numerical simulation applications, you have this complex pipeline. Usually you start from the physical phenomena that you want to model, and this can come from many different fields. So you can have chemistry, you can have astrophysics, you can have finance, biology, etc. You choose a model, a mathematical model, particular discretization, and then you implement it. And again, many choices, many possibilities, which language, which framework, which algorithm. Then you compile it, and possibly you have different runtimes for parallelism. And at the end, you have an architecture. And not all architectures are the same. And nowadays they are really complex if we want to get efficient running time, both in energy and in time to solution. So with this very complex chain, what I'm going to talk about is the challenges we have with floating point numbers, floating point representations. And there are many of them. Actually, we can have loss of accuracy at each of these different steps. At the model or discretization step, we can have discretization errors, depending on the approximations we do, on the conditioning of the problem. Then at the implementation and compilation steps, we have to deal with the floating point formats. So most of today architectures are based on IEEE 754 formats, where we have different kind of errors, representation, absorption, cancellation. But with the big success of hardware accelerators, GPU, now we are moving to smaller formats, which sometimes are a bit more exotic. Interestingly, floating point arithmetic is not associative. So the order of operation is going to matter, and it's going to influence the error. So all the optimizations we are going to do, vectorization, compiler transformation, parallelization, can affect accuracy. So these three points actually show that all these choices we can do to improve performance are going to affect the accuracy of our results. And there is an important trade-off there, because if we can reduce precision, we can save energy and we can save time to solution. And nowadays, the environmental impact of computation is a very important topic. Computational problems are getting bigger and bigger. So we should aim to do the computation with the smallest possible precision that guarantees conversions to solution. Okay, so I'm going to start with a quick presentation of floating point IEEE 754 representation. So we have a standard representation that is very close to the scientific notation we learned at school. So a number is going to be defined with a sign, an exponent that gives it a pseudo significant binary 32, which is usually called float, and binary 64, which is usually called double. And what is interesting about this representation is that it has a large dynamic. It allows to represent very big and very small numbers thanks to the exponent. But that means that actually the errors are not going to be the same when you have a very small number or a very big number. It's what we see on the real line at the bottom. You can see that the representable floating point numbers are much more dense around 0 than when you have a big number. And this means actually that we are going to have our errors are going to be always relative to the magnitude. Okay, one example of the kind of errors we can have with floating point numbers is absorption. Absorption is going to happen when you take a very big number, like the one on the top in this figure, and you are going to add it to a very small number. So here we have a 2 to the power 20 difference between both. So before doing the sum, we need to normalize both numbers so they have the same exponent. And this means that the smallest one, we are going to shift its mantissa 20 positions to the right. Because the mantissa is finite, all the digits in red here are going to be lost. This is what is called an absorption. And there are other errors that can happen. IEEE 754 has some guarantees on error. For the basic arithmetic operations, it tells us actually that the approximation it's going to make, which here I'm going to write hat z, it's going to be equal to the exact result, x round y, multiplied by an error factor. And here we are going to represent the error as a relative error. So we have this delta term, and we're going to say that the magnitude of the relative error is going to be at most u divided by 2, where u is the unit round off, and in fact corresponds to the precision of the architecture. So usually we are going to round, and we are going to round to the closest floating point that is representable. So in the picture below, you see we have the exact result would be z, but z is not representable. So we are going to round down because you see z is closer to the lowest representable than to the highest one. And thus, IEEE 754 default rounding, round to nearest, is deterministic. If we are going to talk about errors, about reproducibility, we need to introduce a bit of vocabulary of metrology. So we have 3 qualities. We have precision, trueness, and accuracy. Precision is not going to tell if our result is close to the real solution, but it's going to tell us the spread between repeated computations. So you see here, we are not in the middle of the target, but the different repetitions of our computation are very close. Trueness is going to tell us when the different computations actually are unbiased, are around the expected real result. And finally, accuracy, the third one, combines both qualities. And it's what we want, actually. We want an accurate result. Usually accuracy, you can measure it directly just by taking your result and comparing it to a reference value. The problem is many times we don't have a reference value. For some problems, physical problems, we have multiple solutions that are admissible. And in other situations, the reference value is unknown. Maybe it's a new simulation for which we don't have a ground truth. Maybe we want to check one particular routine or function in the middle of a big computation, and we don't have an exact or a measured value for it. And how can we proceed in that case? Well, my point in this presentation is that checking precision and reproducibility do not always require a reference. And now I'm going to give the outline. So in the first part, I'm going to present Monte Carlo arithmetic, which is also called stochastic rounding, which is the theoretical underpinning of VerifiCarlo. And then in the second part, I will present the tool and also one of its backend, variable precision, that allows to explore or reduce precisions in computation. Okay, so let me start with a bit of theory. As we saw, each floating point operation may introduce a relative error delta. So the idea in Monte Carlo arithmetic, which was first proposed by Stott Parker in '99, there was, it's an old idea. There was already many proposals before that go back to the first computing architectures, actually. But Stott Parker was the first that formalized Monte Carlo arithmetic. And the idea is to make delta a random variable. So, for example, if we have here three operations that are chained, so two sums and one multiplication, we are gonna have delta 1, delta 2, and delta 3 that are gonna model the errors at each of the steps, and we are gonna consider that the deltas here are random variables. And then we can model the forward error, C, as actually the relative difference between z hat and z divided by z. And we can, and this actually, because it depends on the delta 1, delta k, in fact, it becomes a stochastic process. And we can analyze the error probabilistically. That's the idea behind Monte Carlo arithmetic. So now the question is, how are we going to choose the distribution of the delta k? Okay, so I'm going to write up-round rounding z to top, down-round rounding z bottom, and we are going to choose this stochastic rounding, this Monte Carlo arithmetic rounding. We are going to round up with a probability p that depends on z, and round down with a probability 1 minus pz. And we want to choose pz in a particular way. And the way that we choose this pz is the way that makes the computation unbiased. That means that the expected value of z hat is going to be the exact mathematical result z. So we have only one possibility to achieve this, and is for pz written as z minus z bottom divided by the size of the interval. So in fact, what it means is that we are going to round bottom or top depending on the position of z in the interval. So for example, here, if we have z, and here I take a decimal notation, equal 1,62, and the two closest representatives are 1,6 and 1,7, we see that, in fact, we are going to round down with a probability of 80%, because here we have 62, so we have 20%, 80%, and we are going to round up with a probability of 20%. So the probability of rounding to a representative is inversely proportional to its distance, to its relative distance. And we can see in this simple example that indeed at the end, if we round down with a probability of 20% and up with a probability of, if we round up with a probability of 20% and down with a probability of 80%, we get indeed an unbiased computation. So the average of the different z hats is going to be z. Okay, this is quite nice because it means that our Monte Carlo arithmetic is unbiased. And now the question that we can ask is what happens when we chain multiple operations. So here we are going to chain two operations, so around circle 1 and circle 2. Each one of the errors, delta 1 and delta 2, is unbiased, as we just saw. And there is a very important lemma that was proved by Connolly and others that actually shows that when you chain different operations, you can show that actually the delta Ks are mean-independent random variables. So mean independence means actually that the expected value of delta K, knowing the previous deltas, is going to be equal to the expected value of delta K equal 0 because we know it's unbiased. Mean independence is a property that is between independence, which is much stronger and which we don't have here, and uncorrelatedness, which is a weaker property. And this is very strong because it actually we can use this to show that in many algorithms, we actually have an unbiased result when we use stochastic rounding. So we showed this recently in a paper that is available on arXiv. And we show that actually for all computation graphs that are a combination of multilinear sum products, we can show that actually the error is a martingale. So it's a generalization of a random walk. A random walk requires independence. Martingale can be defined with mean independence. And this is quite strong when we have a martingale because we can show that actually the result is going to be unbiased. And we can use concentration inequalities to actually bound the error probabilistically. And what we show is that for all multilinear sum product algorithms, we have an error bound that is in big O of square root n u. And remember, n is the number of operations in the computation graph, and u is going to be the precision of the machine. This is nice theoretically because it allows us for many basic building blocks for numerical algorithms to give formal error bounds. So for example, for the dot product with stochastic rounding, we can show that we have a square root nu bound. For example, Horner's polynomial evaluation, again, square root nu bound. Pairwise summation, we've got the same, but with a log n. And Karatsuba, again, we have a square root of log n. So this is quite nice, and it allows us directly, theoretically, to analyze algorithms that are multilinear. But what about nonlinear algorithms? And when you get into simulation codes, very quickly you get into complex codes that are nonlinear. What can we do? Well, then the trick is we're going to use Monte Carlo arithmetic, but we are going to estimate the error function with Monte Carlo. So let me give you an example. We have a very simple linear system. Okay, so it's a 2-2 linear system. But here it's very ill-conditioned. So we have a condition number around 10 at the power of 8. So we are going to solve it very naively with Cramer's formula. And you see, here is the result we get when we compute in double precision. And here is the mathematical exact solution. So when we compare both, we can see that we have around 8 significant decimal digits or 28 significant bits, which is expected when we know that the condition number is around 10 at the power of 8. So now, what can we do? This works because we know the reference value. But remember, we want a method that can work even if we don't know the reference value. So the idea is we are going to use Monte Carlo arithmetic. So we are going to repeat the computation, but each time we are going to introduce this small delta as a stochastic rounding, as defined previously. So at each operation, we are introducing a small noise that is unbiased. We repeat the operation many times. We get many different results. Sometimes we have 7 significant digits. Sometimes we have 8, etc., etc. And then we can represent the distribution of these results. And what is actually very nice is that when we compute this value here, which is the magnitude of the signal to noise ratio, we get 28,5. So something very close to the number of significant bits. And actually, we show in 2022, we showed actually, and we gave confidence intervals showing that this value can be used to estimate the number of significant digits without a reference. So that's the idea of Monte Carlo arithmetic, and that is what we are going to use in VerifiCarlo to estimate the number of significant digits of a computation. One last theoretical point before I present the tool is that the default rounding mode, round to nearest, is deterministic, and therefore can become biased for large summations. For example, if the value we are adding is always very small, we are always going to round to the bottom. And therefore, we are always doing an error on the same direction. So these errors are going to accumulate. And it's what we see here with the IEEE round to nearest error with the yellow stars. You see the error is accumulating. On the other hand, with stochastic rounding, because we have this unbiased property, we can avoid stagnation. And that is quite nice because it means that when you use stochastic rounding to analyze an algorithm, we are going to detect stagnation whenever we have IEEE round to nearest that is not behaving the same than stochastic rounding. Okay, so now for VerifiCarlo. So VerifiCarlo is an open source tool. Now it has 6 or 7 years, I think, and it's available at this URL. It is based on the LLVM compiler. It's a specialized pass that is going to come at the end of VerifiCarlo. So in fact, we can compile any language that VerifiCarlo can that LLVM can compile. So we can compile C, C++, Fortran applications. With Fortran, I have to say that we depend on Flang, and the state of Flang currently it's still a bit shaky, but it's possible. It requires some work. It's an active open source project with 15 contributors. And how does it work? I mean, what is the big architecture? In the front end, we are going to compile with LLVM. And at the end, we are going to replace all floating point operations by callbacks. And these callbacks are going to call specialized backends. We have different backends. Some backends are going to, for example, use Monte Carlo arithmetic, stochastic rounding, as defined previously. Other backends are going to allow to detect cancellations. And we have other backends, VPREC, that allows to simulate what happens when we reduce the precision in our computations. So it allows us to measure the impact of reducing the precision without having to change completely the code, to port the code to a different form. Then we run the code, we get some data, and depending on the backend, we are going to do an appropriate statistical test to interpret it. The overhead is quite big. The overhead is quite big. You can see it goes from 6 times lower to 160 times lower. And I will show more details later. One thing about the architecture of VerifiCarlo is that the floating point operations are instrumented at the very end of the optimization pipeline, just before code generation. This means that we are going to capture the effect on accuracy of most optimizations. Here we have a very small computational kernel, which implements actually compensated sum, can compensated sum. The trick in can compensated sum is we are going to correct for inaccuracies, for absorptions, by keeping this C term and re-injecting it in the sum. But this requires that the C term is not optimized, because if you re-inject C here, if you consider that the operations are associative, which they are not, and you take C and you inject it here and solve this, you're going to see that it can be optimized to the naive sum. And this is quite fun because we can capture this anti-optimization with VerifiCarlo. If we compare the no we can see that actually, when we repeat many different computations, here the signal to noise ratio is going to be much smaller for the no optimizations. We have 7 significant digits, but for the optimized version, we have only 6 significant digits. What did happen here is that actually with O3 fast math, the compensation term was eliminated by the compiler, and thus we lost the compensation. So VerifiCarlo can capture what happens in the compiler for accuracy. Okay, as I told you, it's quite costly. When you use Monte Carlo arithmetic, it's quite costly. The slowdown really depends on the benchmark. If we look, for example, for a small instance of the conjugate gradient in the Nash benchmarks, we can see that we have, we have different implementations for the Monte Carlo arithmetic backend, but the best one we have, it has this 160 times slowdown. So it means that when you use VerifiCarlo to analyze the accuracy of a very large simulation code, most of the time you must focus on a small section of the code, because if not, the experiments are going to be impractical to execute. So let me show you one example on an industrial code where we use VerifiCarlo to optimize the accuracy. So this is an ab initio computation on the ab init code. It's a collaboration with CEEC, particularly with Chatelain, Torrent, and Yeder. So ab init calculates observable properties of material, optical, mechanical, vibrational. And we looked in particular, I mean, at the beginning, we took the code and we actually analyzed the sensitivity of all the routines to numerical noise. And we detected that there was one particular routine which does a Simpson integral, which is called SimGen, that was very sensitive to rounding noise. And here you can see a trace of accuracy that is obtained with VerifiCarlo. So you have the significant digits, and we are solving the total energy for perovskite. And you can see that we have a lot of drops of accuracy that happen. So once this was detected with VerifiCarlo, we replaced this integral by doing the summation using a compensated version of the dot product, which is called dot 2, and you can find this on a paper by Ojita in 2006. And after these optimizations, we see that now the accuracy is very good. For most of the call sites, we have 16 digits of accuracy, and there is one call site of the function that is still affected because of a reentrant error. And this is a bit harder to fix because we would have to have the compensation term of dot 2 go through this reentrant call. So we didn't do that here, but it could be done. So the last thing I want to present is variable position. So variable position is a different technique than Monte Carlo arithmetic. It's much cheaper. The idea is that we are going to simulate formats, floating point formats with less precision. So for example, we can simulate single precision, we can simulate bfloat 16, TensorFlow 32, FP 24 on standard IEEE 754 hardware. We don't need to port the code to a GPU. We don't need to change all the data types to use single precision. So it's very quick once we compile it with VerifiCarlo, and it allows us to see what is the effect on accuracy of moving to a lower precision. And this is important if we are exploring the trade-off between energy and precision. So how does it work? Well, we are going to use, the trick is that we are going to use the native types to store our computations. And at each computation, we're going to simulate a rounding at the desired desired target precision. The implementation is tricky because it needs to handle many particular cases like overflows, underflows, denormal values, and all the special cases like not a number, infinite values. The rounding to nearest, we chose an implementation that is not completely accurate, but is fast and provides faithful rounding at worst. And this backend has a lower overhead than stochastic rounding. As you can see, it has at most a 16, 17 times slowdown. Okay, and you can choose any exponent and any precision that is lower than your original hardware data type. One example of VPREC, we used VPREC to explore mixed precision on CFD solver from Korea CNRS, which is called YELS2. So at the core of YELS2, we have a deflated preconditioned conjugate gradient. So we have a CG actually that is going to alternate between converging on a deflated coarse grid, and then when it has converged on the coarse grid, it's going to move to a fine grid to refine, and it's going to do this many times. So what we wanted, our objective was to find a minimal precision over iteration that would preserve convergence. So we did this with a dichotomic exploration, and we can see at first we look at the entire application, what happens when we do on the fine grid and the big grid, and here we show the minimal precision that is required for convergence. And we see that in the middle iterations of the solver, we need more than 24 bits of precision. If not, the solver doesn't converge. So it means that we cannot move to a single precision, which is 24, okay? But then we have this idea, maybe we can use the lower precision only on the deflated grid, because there we don't require as much precision, since we have later the refined grid stage. So we did the experiment, and indeed we can see that on the deflated grid, the required precision is always under 24 bits. So we can rewrite the deflated solver using single data types, and we get gains in energy, gains in communication, and gains in time. One thing that is nice is that once we have moved the code to single precision, we can check how robust it is using stochastic rounding, using Monte Carlo arithmetic. We can repeat, for example, here 30 samples, and we see that for the 30 samples, we always converge. And this gives us confidence that actually, even for small variations, the solution, the mixed precision solution is going to be stable. So I'm a bit longer, sorry a lot, Roman. We have this VerifiCarlo tool based on LLVM that transparently instruments large codes. We have different backends. We have stochastic rounding that allows to do an average analysis of precision. And it's very useful to check for numerical bugs or reproducibility. And we have VPREC that allows to simulate lower precision formats without paying the porting cost. VerifiCarlo has been used in many large codes, ABINIT, DP, Europlexus, YELS2, QMCKL, and others. It's an expert tool. It requires collaboration between the numerical expert and the physicist that really knows his code. But it allows to check for accuracy. And one of its limitations is that it has a costly overhead, as I showed, and also the analysis is data dependent. So usually, if you really want to be confident, you have to check in many different data inputs before getting some confidence that you can move to a lower precision. And now I'm going to give the floor to Roman, that actually with Yang Xian worked on NECBON and NECO using VerifiCarlo. And as I was saying, the results on these slides are not only by me, many people contributed to them, so thanks a lot to them, and thank you.
Well, thank you, Pablo. Okay, let me continue the story and see how it actually we can use VerifiCarlo for our. Maybe we can stop sharing so that I can take over. Okay, now I found my slides. That's the most important part. Okay. Okay, seems to be good. Can you see it? It works? Okay.
Yes.
Yeah, okay, I assume it works. Okay, lovely. So Pablo presented us how we can actually use VerifiCarlo with different backends in order to confidently reduce precision and also to get some kind of error estimate with MCA backend. So here I will show you how we apply it in the CEEC project. So my agenda, I will try to stick to 10 minutes. My agenda is like this. So at first, we have this objective in CEEC project. It's called energy efficient computing that I wrote during the proposal preparation stage. And the idea here is actually to look on how we can achieve it through optimizing precision usage of our solvers, underlying solvers in computational fluid dynamics. This is one angle. The other angle would be to make more efficient solvers, certainly, like to use different parallelization technique and strategies. But here, our particular focus would be on mixing different precision and still assuring output accuracy. I will present briefly methodology of this approach, and then I will show how to apply this methodology to Neckbon's mini app and real world code Neko. So the main idea here is that we are bounded in terms of exascale computing by power consumption. There is a lot of effort going on in terms of hardware. We have different initiatives like European processor initiatives that it would be new exascale supercomputer would be hosted in Jülich based on RISC-V and NVIDIA GPUs. And this is very relevant, but I'm thinking actually I'm coming from numerical in algebra. How can I give a hand of help in this effort and how I can contribute to this? And if I look on numerical in algebra, its predominant precision is double precision. Double precision is there are some routines, but if you look on how applications use it, it's predominantly double precision, and it has some security because we know that we can get a larger span of numbers that we can cover. So in terms of precision, operating precision, and then if anything goes wrong, it's very high chances that we can actually mitigate or capture it with double precision. Yeah, so that's the idea. But if you want to develop energy efficient algorithmic solutions for linear algebra, we need to think about how to mix and adapt precision. So how to make sure that our solutions work for different test cases and do some smart parallelization to avoid synchronization as communication is a killer, and also how to use tools such VerifiCarlo or other tools in order to do profiling to gain high performance in order to detect abnormalities and to guide us how to crop precision. We have prepared this best practice guide because we notice that it's not as easy to measure energy to solution as time to solution. And then here we list different possibilities and our, how to say, top selections to use SLARM or different, basically SLARM as we submit a job and immediately we can get some energy consumption metric. And the other possibility, if you want to dive deeper, we propose to use some tools like Liquid developed in FAO in Germany. So our idea was to facilitate energy measurements on European systems. Not many systems actually support this openly. And why openly? Because sometimes it's possible to get energy measurements if you are working inside the cluster and you are a trusty person, so it's quite interesting. But if you are outside, so sometimes it could be quite difficult. And we provide some examples with easy to use guide. So here I will be going through some of these examples. We actually covered all the codes that we mentioned we use in CEEC. So that's quite nice and good to check. Our methodology is like this. We have original application. We discuss with experts and developers, and we pinpoint or we just do profiling what are the main time consuming parts. And usually it's pretty much nearly to the 80-20 rule. So 20% of code consumes 80% of time. So that's roughly it. And quite often we will end up in some numerical solvers like conjugate gradient, iterative solvers, or different ones. So then we try to use arithmetic tools like VerifiCarlo in order to pinpoint this time-consuming regions and in order to simulate different precisions there with using VPRAC backend as Pablo presented. After we have identified these code sections that have potential, we can actually move to the mixed precision after this verification, and we then can validate in the application and see how it actually works. So one example, I start with a simple code. It's like Neckbone is a mini app, so it solves Poisson's equation for pressure. It's just simplified. There is not much physical meaning, but it is one part of solving Navier-Stokes equation for incompressible flow simulation. So it's like quite good motivation to start from there. And the basic solver there is preconditioned conjugate gradient. We start without preconditioner. Here's a loop, and we focus on particular functions that are very sensitive for precision. This raw, where we compute a dot product, so we involve some global communication. We have tau that computes residual stopping criteria, and we have another component beta. So our particular focus here was on a computation of residual. So what we did, we use VPRAC backend, and we try to look on the value of residual axis y, and we try to mitigate different number of bits. So we stick to mantissa of double precision, exponent to double precision, but we were varying number of bits. Well, what we can see is that we have some perturbation over here, but then we have a plateau. Plateau means that throwing more precision will not help you to converge because it's just enough. We will also simulate in different number of elements because it's a spectral element method, so more elements naturally is better for simulations, for output. But from the picture, what we can see is that we can safely reduce precision is for the entire application up to 16 bits. So nice, fine, and we will still have some, how to say, cap for accumulated errors until we reach limits of single precision. Then we did another simulation like testing sensitivity with MCA backend. So basically doing some perturbation using random rounding on the left seems to be fine, but then when we did a bit more, inserted a bit more noise with MCA backend, we can see that we stop converging. We pinpoint with help of VerifiCarlo and a profiling tools that there is some initialization stage 10 to the power 9 multiplied by cosine, so it actually requires higher precision and it actually perturbs the whole simulation. So our conclusion was that to leave initialization double precision, but the solver, the most time-consuming part that consumes more than 80% of the whole simulation in single precision. This led to be a good strategy and seems to be working very nice, and we have convergence. Then next step is to enable preconditioner, and preconditioner is multi-grid preconditioner. So this is pretty much a game changer, as in majority of CFD simulations. So preconditioner is very strong. So solver runs several iterations, but preconditioner may consume inside the solver 70% of execution time, as in this case. And we have noticed that with the preconditioner, we have stagnation. This stagnation is on the left was predicted with VerifiCarlo using MCA backend, and then it was confirmed when we run it simulation. So we have some stagnation. Here is actually, we can open a discussion. Is it enough 10 to the power minus 6 for the simulation? Can we stop and proceed with our simulation? Sometimes yes, some simulations stop at 10 to the power 4. It's a residual for the solver, but for some we may need to have higher accuracy of simulations, especially when we have this fine meshing. So we then again use the tool, and then we pinpoint surprisingly to us that the reason for that is a square root operation that there are a couple of occasions that they occur in preconditioner. So we did a span of like Andy Warhol picture, so to try to observe what would happen. We have sequential on the top left corner, and we can see that when we compute this square root operation in double precision, we actually get convergence. Stagnation is represented here with blue line. Then we started increasing number of MPA ranks. So 2 is still good, still have convergence. 4, something does not work. We have this red line that is actually repeat stagnation, but a bit lower bar. Then we naturally increased number of MPI ranks, and then we can see that overall we still have stagnation with high MPI ranks. So bam, 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 the issue is in communication. So then we pinpoint the communication, what is happening, and then we notice that the issue is actually happening in this global communications, that is gather scatter communications. This is how communication between different domains is conducted. We have two types of communications. This gather scatter communication that is working as a library, and it has different modes. Here we are considering pairwise mode, that is actually the most performing mode. And there is another communication that is happening within preconditioner and conjugate gradient method. So it's like this global reductions to compute dot products. So we try to see different cases, small number of core counts, large number of core counts, and then we pinpoint a successful strategy. So obviously, if you compute preconditioning completely in double precision operations and global communication, everything is converging. But this is not what we want, because our idea is to have some gain, since preconditioning is already consuming 70% of the execution time. So we try to see what can be done. We know that square root is causing us some problems, so we start to keep all operations in preconditioner in single precision, square root in double, and also communication in double, both in preconditioner and in CG. CG operations can be safely conducted in single precision, and we have conversions. So this is our winning strategy over here. The other winning strategy to use different kind of communication called all reuse. And with this winning strategy, we conducted measurements through Euro HPC-GU development access on Mare Nostrum 5 and on Lumi. And here we present some results. We have two strategies. One is based on all reuse, when we can actually keep communication in single, and the other one in pairwise, that we have to do communication in double. We can see that it seems to be quite appealing to keep communication in single. However, in terms of performance gain, it's not so drastic. So all reduce is quite heavy. We need to reduce everything and then distribute. So it's much more expensive than pairwise, still on one node. And pairwise, if we use half a node, we get 37% of reduction. But when we use the entire node, we get 2.x reduction. So it's quite huge gain. When we looked on energy consumption, there we were using EAR tool from BSC. We have close collaboration with BSC, and we measured is pretty much a few days ago when we prepared special issue submission, and you can see that the gain is still there. And the gain is actually quite big. The gain on the full node is actually quite questionable. So we need to explore why it's so huge. So I think I will stop it here.